So we're going to go ahead and take a look at 1.8, but sometimes in the transition I start talking about things. What was I talking about? So we go till 10:15. Is that correct? Okay. So, and again, next week we'll be have a little bit more leeway because we've only got 3. We've really done 4 sections this week, so 2 each day. Next week we'll be able to ease up a little bit. We'll just have to do 1.5, which means maybe we'll do 2 and then just 1 on. So Thursdays will be a little bit later. Thank you. That's where I was going, and I forgot where I was at. So I was talking about, yes, tutoring. So Wexler Hall, and that's because you guys are in a STEM field. They're really good at that type of tutoring. Some of like my business majors, I tell them to go to the business because that's where they get better tutoring for their needs. But the Wexlers are your math majors and your technical majors, so they're well suited for this class. There's also online tutoring that you can get to. There's a lot of hours, so those are accessed based on the course and such. So take advantage of those. But thank you for the plug. It was getting me back on track. Okay. Inverse function. So let's backtrack now. I am recording. Good. An inverse. What does an inverse do? I do something and I get up here. What is the inverse going to do? It's going to undo. It's going to take me back. So in a function, what happens in a function? I have some x that I input. I do something to it, and I get a y value. So input, output. So what would an inverse function do? And I'll write it with the notation. So it looks like f to the -1 power, but it's just their way of writing inverse. So f inverse, what would the inverse function do? Where does the inverse function start? It starts with the output. So technically this has always been confusing. And it's going to take y, and where's it going to put it? Back to x. It really, literally, an inverse will, mathematically, it'll switch the x and the y. So the function takes x and sends it to y. An inverse is going to take y and send it back to x. So it kind of reverses it. We will oftentimes we will graph a function and its inverse function on the same xy axis. But remember, just like we were talking with composition, the inputs are different. The inputs to an inverse function are the outputs of the first function. So it's really, I've got some colleagues who says you should never do that. You should never graph them on the same set of axes because this x is not the same as that x, but we do it. And it's because we're going to see that it's kind of pretty. You get this reflection around the line xy, and so it gets done. And it gets confusing because what they'll do is they'll do this, and then they'll say, well, here's the inverse function. But again, those x's, if I'm talking the inverse function, that x in the inverse function is not really x, it's y from the original function. But we use this notation. And what I like to do is address the areas where you may be experiencing some cognitive dissonance. That's a big word I learned from Psychology 101. But that psychological dissonance is you say, this doesn't seem right. And you're right, it isn't. But it's just kind of conventions that we go with. Functions, we always are putting x as the input, so let's stick with that. Some curriculum have changed it. I've seen them where they're putting y as the input, and so then it's actually more accurate, but it's harder to deal with because the way I learned is to go with the x's. So I'll be honest, I haven't looked at my math lab, but I'll bet you they're still going with the x's. That's how the ALEX system works. So we'll see where we need to go with this. But so the thing is, if I have a point, if there's some function f of 2 goes to 3. What do I know about the inverse function when I plug in 3? It's going to be 2. So that's really, you'll see questions like this. So if I know input gives this output, when I go for the inverse, I just need to switch them, right? And we'll see how that comes about. Okay, so the inverse process. Math is filled with inverse processes. It undoes what the original does. So I can't remember what my notes all say here, but if I go with addition, what is its inverse process? Subtraction. We've been doing that. If I add 5 and then I subtract 5, I got back to where I started, right? So, and it's subtraction, the inverse of subtraction's addition. So it's kind of like they're pairs that work with each other. If I multiply, what is my inverse? Division, right? Multiply by 3, and then if I divide by 3, I've undone the first thing. I'm back to where I started. We're going to see, we don't get to today, but exponentials also have an inverse, and that's a logarithm. So, but we'll come back to this idea of inverse functions when we get to logarithms, because that's the only really way that I can understand what a logarithm is. It's the inverse of an exponential. But exponentials, I don't really understand. I mean, we don't memorize tables of exponentials. We do, you know, we got multiplication down, hopefully pretty good. We got addition, subtraction down pretty good. Those are good. But we never, you know, memorize tables of exponents. And so that makes exponents and logarithms a little more difficult. So there's a forward process and an inverse process. And again, we could say addition, subtraction, or we could say subtraction, addition. I'll get these out of here. So if I dig a hole, what would be the inverse process? Fill the hole. If I fill a pool with water, the inverse is to drain the pool. If I delete a file, hopefully I can undelete it. So I guess I could write these: dig a hole, fill the hole, file. That should be fill. Fill a pool with water, empty the pool, or drain it. Right. Delete a file, undelete, hopefully.
You can recover.
You can recover. Good. I've had a couple where the disk went down, and I've tried. I probably could have paid somebody to recover it, but I didn't want to pay that much, so I just threw it away. So what is a forward process of a function? It's whatever. Take that input, put it out. So again, we're going to see, we did this one earlier, right? We had a square root, we squared it, they undid each other. Those are inverse processes as well. Which one's the forward process? It just depends on perspective, right? Whichever one you want to call the forward process, the other one is the inverse process. So you think square root is the forward process, squares are the inverse, or the other way around. Just, it works both ways. So here's an example of a linear function. Now, again, we're talking sort of about simple inverses, but whenever we have a function, again, what would be the inverse of this function? Yeah, I think it does. So the first step, I guess, is what I do is I rewrite f of x. Function notation's kind of cumbersome to work with, so we write that as y, right? So this is still the same function. It's just instead of f of x, I'm writing y. Y equals that. So nothing there. First step is what is the inverse going to do to the x and the y? It's going to switch them. So if I switch them, and again I can't remember exactly what my notes do. If I take the y and make it an x, and I take the x and make it a y, what do I have now? I have the inverse function. This is it. But it's not in standard form because it looks like it's the same thing. So what I do is I'll solve it for y, and this is where it's kind of confusing. Then I'm using this x as, but notice this x is actually an output here. Over here it's an input, but if we kind of get past that, if I solve this equation for y, that's what the inverse function is going to be. So I will get y by itself. I'm going to add 5 to both sides. And you kind of see with these linear functions, the inverse is sort of what you think it is. It's the backward stuff. So notice I was taking x and I was subtracting 5. Now I've got x and I'm adding 5. So what you're going to see is you're going to see the opposite operations, but you're also going to see them done in the opposite order, right? Because the first function has, I multiply by 2 first, and then I subtract 5. What we're going to see is now I'm going to add 5, the opposite, and then I'm going to divide by 2. So the order also will change. It always happens that way. And these ones, again, you can see them fairly clearly. Some functions you can't always get a little bit more complicated. You can't see it. Let's divide both sides by 2. So then I'll switch the order here. I get y equals x plus 5 over 2. And what I do is now I go back to function notation. I change that y to being f inverse of x equals x plus 5 over 2. And again, that x is really the y from the first one, but we'll deal with it. A lot of times they want it this way. So I've got my inverse function and I've got my original function. So just sort of rewrite it as function notation, write it as y, switch the x and y. That step makes it an inverse, and then we solve for y just to make it look pretty and to have it and be able to put it in inverse function notation. Okay, you need to get the y by itself. I'm going to try something. What's our timing? Yeah, we're okay. What would happen, do you think, if I took a composition of two functions that are inverses of each other? They would cancel. And what does that look like? So if I took f of f inverse, when they cancel, you're right, they're going to undo each other, right? Where does the function start? It's the first thing we do with a function. The input, right? What is the input? X. We're going to do it and then undo it. Where do we end up? Where we started, X. So if we do a composition, this is just kind of a tricky. If we do a composition of two functions that are inverses of each other, when we're done, we end up with just X, which is kind of weird, but that's what we started with, right? We started with X, we end with X. So let's try this here. So the f inverse is going to be x plus 5 over 2, right? The f function is 2x minus 5. I plug in the x plus 5 over 2 into here. And now I simplify. 2 divided by 2 is 1. So I get x plus 5 minus 5. Well, 5 minus 5 is 0. X plus 0 is still x. See how it worked? We started at x. X was the original input. We end up at x. These are inverse functions. So there's a way, and that's part of probably what I've got going on further. But I just wanted to tie the two together. Once I find that inverse function, if I do a composition, I will always get just the value of x. Not negative x, not x plus 4. I've got just x. Of course, yeah. Yeah, if you have to head out anytime, you're always welcome. Okay, square root function. So that's kind of one we looked at. And again, sometime in the square root, we have to restrict the domain, because if we get a negative inside of a square root, it's an imaginary number. Sometimes we use those. So find the inverse. And again, what we're going to do is we just start off with the function. We rewrite it as y equals square root of 5 minus x plus 7. So all I did is change the f of x to y. That's all I do, just to make it easier. And then the next step is to switch the x and y. Now, if you read through the instructions in the text, sometimes they will do it in different orders, but this is the order I've always found, because this is actually when I switch them, that is what the inverse does. I have the inverse as soon as I switch the order. This is now the inverse. Again, what I want to have y equals, so that I can say that that's the inverse function. But this is, in a way, the inverse. And our graphing tools are getting better. There's graphing tools that will actually graph that in that form. So now I need to solve it for y. What do I need to do? I need to square it, but if yeah, let's get rid of that 7 is kind of hanging out there, so let's get that out of there. This is what I mean. Some of them become a little bit more complicated. Okay, so I isolate the square root.
But then we can square.
Now I can square both sides, and it's going to be smoother. So I'll square this side, and I'll have to square this side.
And I have a question. If we square root the like in the square, don't we need to put the absolute?
You could, although we do that when we get to logarithms a little bit more. They always put that, but I think we could. Yeah, I think we were able to be a little sloppy, but technically we should. It does need to be positive in here. So we get 5 minus y equals x minus 7 squared, which you could FOIL out if you wanted to, and maybe you'll need to in the homework, but I'm going to, just for the sake of being simplified, I'm going to leave it. We would subtract 5 from both sides. And so what we get is we get minus y equals x minus 7 squared minus 5. And then, but I want not negative y, I want positive y, so I multiply both sides by a negative. Get y equals negative x minus 7 squared plus 5. And I could call that the inverse. And again, I might need to, because of how they want the homework, they might want this simplified or FOILed out and then like terms combined. But sometimes we want to leave it in this form because it's maybe more meaningful. It's I think this is the vertex form, right? If I remember rightly. So I actually could see that. I believe that's going to give us a vertex negative 7 plus 5. But that's it. So what's the domain of the inverse? Now this is where it gets a little tricky. What we want to do, we know the domain of the function that we started with. So and the domain refers to the x, so what's the domain of the forward function going to be in relation to the inverse function? The domain will be the range of the inverse function, because this was the x and now it's the y. So that's an easy way to kind of do this. So I know the range over here. Of course, I'm not asking for the range, but I know the range will be negative infinity to 5. But what I could also say is the range, or the range of the original function will become the domain of the in function. So looking up here, what's the range of this function going to be?
Negative 5 to positive infinity.
Let's do this. Range is oftentimes best analyzed by looking at the graph. So and again, we could, because if we come back here and we just look at the in function, we might say I could plug in this x, I could do anything, right? But since the first one has a limited domain, it may also have a limited range. What was the function? It was square root was it x minus 5, right? Or 5 minus x. 5 minus x. That's right. and then there was a plus 7. And I don't see anything because it moved up here. But what I can see is the range is going to go from 7 to infinity. The y values, right, is going up to positive infinity, so it's going from positive 7 to infinity. That's its range. And so when I come back here, I can say that the domain of this one is going to be 7, not negative 7, positive 7. To positive infinity. So that answer, yeah, maybe I'll put it up here. 7 to infinity. So when we've got these questions, sometimes it's hard to answer from one of the functions to the other. Because notice, do we need to restrict x? If I just look at this inverse function, x could really be anything, right? Because it's going to be a quadratic. But because the original function that it came from had a limited domain, it's also, for the two functions to work together, this one's also going to have a limited domain for it to be able to work. Okay, so we limit the domain to just 7 to infinity. And if you see that, you put in 7 minus, that's going to give us a 0 here. We'll be at 5, and that way it will be able to be plugged back into this. And then with the negative, it keeps it so that the two functions can work together. Okay, so when we're talking about functions and their inverses, we are in a context that in order for these to work together, we have some limitations. A quadratic does not have a limited domain. It's negative infinity to infinity. But if it's working in concert with its inverse function, then we're going to have to limit it. All right. How are we doing on time? Let's see, we're almost there. Let's take a look at this one. It's a little more complicated. It's harder to see, but let's take a walk. Oops, no, I don't have it. So y equals 2x over. Actually, you know what? This one's a little complicated. Let me do this. I'm going to save this example because it's got something you've got to see, and it's probably taking us about 10 minutes instead of 5. But if we do it next Tuesday, it'll all make sense. Let me just show you the difficulty here. When we switch the x and the y, what do we end up with? We end up with 2 y's. And what we're going to do is we'll move them around, but it typically will involve some factoring to factor out that y to make the 2 y's 1 y. And that's where the complicated step comes in. And if I try to rush through it, I'll lose probably half of you, and maybe I won't ever get you back. No, we'll get you back, but it'll be better. Let's wait till Tuesday and do it when we have some time. All right? But thank you all. Have a great weekend. Enjoy the summer heat again. I was